Hello class, welcome to our final segment, segment 7 from chapter 4, where we've been talking about ratio and regression estimation. We're going to end this chapter with a discussion of regression estimation. It's a generalization of ratio estimation where the underlying relationship between the variable that we want to estimate, the y variable, and the auxiliary variables that we might have available for use they're linearly related, but it's not regression through the origin per se, but it could be any general linear relationship. And so we're going to work through an example here, and then I will talk to you about the estimators, and then how to calculate the standard errors, the estimators themselves, and then how to use R to get this information. So when you don't have a regression through the origin situation, you're going to, and you have an auxiliary variable available for all of the units in the population, then you could use a generalization of ratio estimation called regression estimation. And this is really, if the relationship between X and Y is negative rather than positive, regression estimators can certainly provide more efficient estimators compared to those based on sample means alone. So it allows you to generalize that use of ratio estimation for the cases where your auxiliary variable may be linearly related to your outcome variable, but it may not be positively related or through the origin. The regression estimator, very much like the ratio estimators, will be biased, but again, the degree of the bias can shrink under certain conditions, namely around those conditions that we talked about for ratio estimation that really govern the strength of the relationship between the y variable and the x variable in particular. So in this framework, we're going to assume that we have this kind of model in the population. So we've got the capital Y variable, which is all the outcome variables for any unit in the population. B0 is the intercept of the regression line that goes in the population. B1 is the slope, and X is the auxiliary variable. Under simple random sampling without replacement, we can estimate this B1 by B1 hat, and that's simply the correlation between the Y and the X variable in the sample, multiplied by the ratio of the standard deviation of the Y variable in the sample to the standard deviation of the X variable in the sample. These are very similar to the calculations that you would do in your regression course if you've taken a regression course already. Now keep in mind that this B1 hat is a sample estimator for the true population slope here. And remember, this regression line could essentially be calculated from a regression that is performed on all the y variables and all of the x variables from the population. You estimate that, and that becomes your model, so to speak. Notice that there is no error term here for those of you who have seen regression or are taking regression now. There's no error here because, again, we believe that this is determining the relationship between y and x in the population. It is though it is already observed. We don't have an underlying model that's generating this per se. We don't talk about normality here. But again, we believe that there is a linear relationship that one could ascertain governed by these two parameters, B0 and B1, in the population that relates y from x. And that is the sort of idea. Now, the other part here is the B0. So the intercept estimate is going to be the sample mean minus the estimated slope times x bar, which is the sample mean of the x variable. And we compute the regression estimator by simply predicting the outcome of this regression line when we fix the x variable at its population mean value. So in other words, when I hold x equal to x bar u and then multiply by beta 1 hat and then add beta 0, I'm going to get what I'm calling the regression estimator. If you put this x bar u as the population total, you would get the regression estimator for the total if you knew the total. And so that is the idea. So the approximate standard error for y-bar regression under certain conditions, obviously, with sample size and so on, is going to be approximated by this formula, which we've seen already in the ratio estimator. This E is a residual, and the residual is the observed value in the sample minus its estimated value from the regression line. So that's B0 hat plus B1 hat times the X component. This is nothing more than the observed minus the predicted mantra that you've seen in your regression courses. So this is the EIs. I'm going to take the sample variance of these EIs. The mean is virtually 0. And then I'll divide by n, and then I'll multiply by the FPC, take the square root. That's the standard error. You have seen this formula from chapter 2 in chapter 3, and you've seen it in this chapter several times. You should be getting this down pat by now. In small samples, you could use the mean squared error term that you get from a sample regression of y on x using the sample data, which basically accounts for changing the denominator in this SE squared to n minus 2 rather than n minus 1, and it provides a more stable estimate of the variance for a small sample situation when you're doing sampling without replacement. So keep that in mind, and we'll talk about that as we go through an example in a moment. The approximate MSE for the regression estimator will again be small if your overall sample size is large. If your overall sample size is large, the FPC is typically going to be driven down. The standard deviation of the Y variable in the population is small, and then the correlation between the X and the Y variable is close to the extreme value that it could be, which is plus or minus 1. Let's look at an example here and walk through the mechanics of how we could actually compute this. And then we'll go through how to get this in R. This example 4.11 data is available in an Excel file with the same name, example 4.11.xlsx. That's in our datasets folder as well as the course notes folder, so you can follow along later as we go. Interest is given in estimating the height of members of the Falcon Villa population. We suspect that height is related to weight. Using a simple linear regression model, we assume that even with small weights, you would still have a minimum height. So imagine, right, if you're a baby and you weigh in the ounces or in small number of pounds, you are still 20 inches long or 15 inches long or whatever it is. And so you don't really imagine that there's going to be there's not anyone in the population that has a 0 weight. So going through the origin is probably not realistic, and so the regression estimator here is probably a little bit better. Now, if we look at this graph, we've just basically, this is the graph in the population. I've plotted all the points, all 24 of the members of the Falcon Villa population. You can see that the apex here, or the origin of this graph, is not 0, 0, so keep that in mind when you are looking at this. And you'll notice that there is kind of a linear relationship. We can imagine a line going through these points and sort of governing the relationship between height and weight, and it looks fairly linear. So in this case, our Y variable of interest, the outcome that we care about estimating, is the height of the members in Falcon Villa. So in this case, we would write Y is the height, X is the weight. And if you weren't sure, you could look at this graph and you could see that I have juxtaposed the graph accordingly, where on the x-axis I have the weight variable and on the y-axis I have the height variable. This is really important to determining this because we are trying to get an estimate of the population mean height. We're going to get that estimate by either a simple random sample estimator, y bar, or we're going to use a regression estimator. We're going to explore using a regression estimator. In this example, you're encouraged to calculate the corresponding y bar estimator and its standard error as we go, and you can compare what happens to the precision of our estimator when we actually take advantage of this linear relationship that we know exists in the population. So from this example, we've got 4.9, example 4.9 data. we have a sample of size 10 that we've taken from 24, and we're going to be able to calculate a few statistics. Again, the data set as well as these statistics can be found in example 4.11.xlsx on our course Canvas page. The sample correlation between the two variables, height and weight, was a little over 0.84. The standard deviation for the y variable is given here as a little over 4. Standard deviation for the x variable is 21. And the y bar in the sample was 68.55. So that would be our y bar estimate. The x bar is 156.7, and that's from the sample, not the population. The population average weight is 150. So using these statistics, we're going to estimate a few things. First, we're going to estimate our B1 hat. Now, why do I do it in this order? Because B0 hat appears first in the formula. Well, B0 hat is a function of B1 hat, so I must calculate B1 hat first in order to actually calculate the B0 hat. So let's proceed. B1 hat is the product of the sample correlation and this ratio. Now, if you don't remember what goes on top and what goes on the bottom, just remember that this is the ratio of y to x. When we did ratio estimation, it's always y to x. That's why it's really important to identify what's the y variable, what's the x variable. So from the statistics that you have up here, this is just simple math now. You can do the math and you can see that the slope estimate is about 0.165. The B0 hat proceeds similarly, where we take the y bar from the sample, which we've already said was 68.55. We subtract from it the B1 hat multiplied by the x bar from the sample, and that was 156.7. So if we add all these things together, we get 42.6827. So now our estimated line is 42.6827 plus 0.165 times x. That's the estimated regression equation that we're going to be using to generate the regression estimator. So putting these together, you can see we have the regression estimator is simply the regression equation, but fixed for x bar u. So in this case, we know that the B0 is 42.68. We know that B1 hat is 0.165. And we know that x bar u is 150. Now I haven't rounded here because these are big numbers, and if I rounded them each individually and then I rounded the result, I could actually potentially have round off error. So I don't want to round these things until the very end, and the software won't do that either. So if you're getting a little bit of a discrepancy in the point estimates between what you're doing by hand and what you're doing in the software, keep in mind that if you've rounded at any step of the way and you're dealing with large numbers here, you could very well be exhibiting round-off error, and so you've got to be careful about that. So the estimate for our the regression estimate based on the sample for the height in inches for our population is 67 and 0.44. Now to compute the standard errors, we need to compute the variance of the residuals. So the way I did this is, here's the information that you have. The residual is the y variable, which is the height, minus its estimated value from the regression. So the way I would calculate the estimated value from the regression is I would take the B0 hat, 42.6827, plus 0.165 times the 162.69. So let's say here the y1 hat, that's for ID number 5, so let's put that as this. This is going to be equal 42.6827 minus, or I'm sorry, plus 0.1650753 times its weight value, 162.69. The residual value that I'm going to calculate in this far column is the difference between the actual height, which is 72.53, the observed, minus the predicted, which is just computed above. I'm going to do this for every one of these. So we'll do one more. Y hat 11. This is going to be the 42.6827 minus, or sorry, plus 1650753 times the weight variable 163.09, and that would be E5. The E11 would be then the value that you get for this sampled element on the height variable, the one we observed, 67.32, and subtract from that the actual value that we estimated from the regression equation, and so on and so forth. Once I've calculated all of these e's, I can then take the variance of them, which is exactly what I get if I do this part here. The standard error of y hat then proceeds by looking at the FPC. So remember, the standard error of y hat regression is the square root of the FPC, 1 minus 10 over 24, multiplied by the sample variance of the e's, 5.064277, divided by the sample size, and that's going to give you the 0.54352 that you see in the Excel folder. All of these are worked out in the Excel file as well, so if you didn't follow this math here, you can look at the Excel file as well for an additional resource. In comparison, the standard error of the y-bar estimator, which I've encouraged you to calculate on your own and confirm that this is indeed correct, is almost double. So we can see that the correlation between height and weight in the sample alone was 0.84. It's quite strong. In the population, it's around that value as well. And so you can see that that strong correlation, a reasonable range on the y variables, the standard deviation on the y variables was quite small. It really implies that this is quite a strong case, even though we have a small sample. How do we get this in R? We can take the linear regression. We can actually create a linear model here, and I'm going to get the exact same values that we got before. So you can see that here. And then I can predict with the weight. I can keep the weight fixed at 150, which is the population value x bar u. And then I can use the predict function, take my regression model, and then which I'm calling the LM. So this would be called regression. I would assign that REG. And then the new data value that I want to use, and I get the regression estimator. If I wanted to do an ANOVA to get the MSE, because this is a small sample and I wanted to get a slight improvement on the standard error estimate, I would take the MSE, which is the residual sums of squares divided by the degrees of freedom. That gives you 5.69. This is what we will use for the S squared E in the equation for the standard error. And you notice that this value is a little larger, which means we'll get a slightly more conservative estimate of the standard error. So the variance for the y-hat regression is again the FPC multiplied by this new S squared E value based on the regression, and the MSE divided by the sample size gives us this number, and then the standard error is just the square root of that, and the standard error is, as I said, a little larger, a bit more conservative. Now, there are a couple of ways to do this in R, which I will tell you about in just a moment.